Oh, by the way, so before I go to the n dimensional case, I want to, so I made a remark in the beginning that x and y, x1 and x2 being both marginally Gaussian does not mean that x1 x2 is a bivariate Gaussian, right. So, I just want to give an explicit example show that that is not the case. Okay. Let us say here example, let y1 y2 be IID random variables distributed according to the PDF f y of y equal to square root of 2 over pi e power minus y square over 2 for y greater than or equal to 0 and 0 otherwise. Okay. So, this is how this, so this is a PDF, this you can actually clearly you can integrate this and see that this is a PDF and y1 and y2 are independent and identically distributed according to this PDF. So, if you look at this PDF, what does this look like? It is a one side, it is like Gaussian with one side chopped off, right. It looks like Fy looks like this. So, it is as though the negative side of the Gaussian has been chopped off and all its mass has been put on the positive side. So, actually what you are doing is taking a Gaussian and taking its absolute value, right, that is what this random variable is. So, this is Fy of little y versus y, right. Let so these two are IID, W equal to plus 1 with probability half, minus 1 with probability half, be independent of y1 and y2. Okay. Define x1 equal to wy1 and x2 equal to wy2. So, I am constructing an example here. Okay. So, what will be the marginal density of x1? So, for x1 I am generating y1 according to this distribution and then tossing a coin which will either come up heads or tails plus 1 or minus 1 with probability half, right. So, my x1 will be equal to the value of y1 with probability half or minus y1 with probability half, correct. So, my density of x1 will have a density. So, you can show that the density of x1 is with probability half it will have a density like that, with probability half it will have a density like that, right. So, you can show, I think this is right, I think I am not making any mistakes, tell me if I do, x1 is n01, okay, and similarly x2 is also n01, same argument, okay. So, both x1 and x2 are marginally standard Gaussian random variables, right, they are marginally both Gaussian, but the contention is that but x1 x2 are not is not a bivariate Gaussian, okay. In other words, they are not jointly Gaussian, okay, is not a bivariate Gaussian. Why is that?
X.
No, x1. So, I am looking at the vector x1 and x2, right. So, in order to show that something is a bivariate Gaussian, I need to show that it has a density of that form, right, v minus 2 rho xy whatnot, right. But clearly x1 and x2 cannot possibly have a density of that bivariate form, bivariate Gaussian form. So, if you notice, so the same W is feeding to the signs of x1 and x2. See, y1 and y2 are always positive, correct, always non negative, and W decides the sign of these x's, but the same W feeds in here, right. So, if my W is plus 1 here, it is also going to be plus 1 here, which means if I look at my x1 and realize that it is positive, then I can immediately say that x2 is also positive. There is no way that x1 and x2 will have different signs. In other words, so which means that if you just plot little x1 and little x2, the joint density of x1 and x2 is constrained to the first and third quadrants, correct. So, looking at x1 alone is a standard Gaussian, x2 alone is a standard Gaussian, but the joint density is only constrained to the first quadrant and third quadrant by construction. The density is 0 here and here, agreed. In particular x and y, x1 and x2 are certainly not independent, right, but and the density is only constrained to the first and third quadrant, which means you do not have a situation like this. If it were jointly Gaussian, then you will have contours like this, right. I mean, there is non-zero mass everywhere, no matter what your rho is, you have non-zero mass everywhere, right. So, this cannot possibly be a bivariate Gaussian.
If x equal to y, both are Gaussian side.
Random variable x equal to random variable y, then it will be a line, right?
Then so that's a case of a degenerate, that's a degenerate case, okay, that's the case of rho equal to 1 actually. So they are perfectly correlated, so all the mass is sitting on that line.
Does that qualify for this?
Jointly Gaussian?
It's a degenerate case which qualifies, okay, it's a degenerate case. So we will talk about joint Gaussians in n dimensions also, where you will get situations where in n dimensions the density may exist in a subspace of k dimensions. So, in that case you can just treat it as a k dimensional Gaussian. So, in this case, yeah, so that is what you do normally, okay. So, is this clear? Is this example clear? This is very instructive because it says that bivariate Gaussian is saying more than saying that they are marginally Gaussian. Okay, so in the n dimensional multivariate case, so we will define for n dimensions now. So there are 3 equivalent definitions of a multivariate Gaussian or a joint Gaussian, okay. So my x is so column vector of n random variables, x is said to be a multivariate Gaussian or jointly Gaussian, x1 xn are said to be jointly Gaussian if it has PDF fx of x equal to 1 over square root of 2 pi to the n determinant of v e power minus x minus mu transpose v inverse x minus mu divided by 2, where mu is a real vector and V is a positive definite matrix. Okay. So, we are just putting down the same formula in n dimensions. Okay. And of course, so I have not yet so from here, so this is a PDF, you can show this is a valid PDF by making some appropriate substitutions and integrating it out. What we can show is that mu is the vector of expectations, expected x1, expected x2 and so on, and V is the covariance matrix. All the diagonal elements will be the variances and the off diagonal elements will be the covariance expected xi xj terms, okay, covariance xi xj terms. Okay. So, this is one definition which explicitly specifies the PDF. So, if you want to check if some vector is a joint Gaussian vector or multivariate Gaussian vector, you go and see if it has this form for some positive definite V and some vector mu. If it does not, it is not, if it does, it is. So, this is the most explicit specification of a multivariate Gaussian. However, this is very messy to work with, right. Even in 2 dimensions, if you write this out, it was a tremendous mess, right. So, this is not very, I mean, it leads to tedious integrals and tedious computations, right. So, often there are equivalent definitions, there are actually 2 more equivalent definitions which are commonly used, which I will also put down, okay. But the thing is, if I put down multiple definitions, you have to show that they are all equivalent, right. So, I am going to put down 3 definitions. So, I have to show how many implications, 6 implications altogether, right. So, I will not do that, but I am saying that you can do it, okay. Definition 2, first line is the same, x is said to be a Gaussian vector if it can be expressed as x is equal to d w plus mu, where w is a vector of IID n01 random variables. So, this is an equivalent definition. You say that x is a multivariate Gaussian if it can be obtained by a affine transformation of a IID Gaussian vector. So, this W is something you can perfectly understand, each of the entries is standard Gaussian and they are all independent. So, W1, W2, Wn they are all IID n01 random variables. You take that vector and perform this affine transformation on it. D is some vector, so D is a matrix. So, for some matrix D, so D is some matrix, okay. So, it is some affine transformation of mu is a real vector, mu is in Rn. Okay. You can show, so you can show that, I mean, you can show the equivalence of these 2 definitions, okay. and in fact you can show that D transpose or D transpose, I think D transpose will in fact be the covariance matrix. Okay. Yeah, D transpose is the covariance matrix V. Mu will be the mean vector. And definition 3, so definition 3 is probably the most cryptic, but probably the most elegant also. So, x is said to be a multivariate Gaussian if for every a vector a in Rn, A transpose x is a Gaussian random variable. Okay. So, this definition says that x is said to be a Gaussian random vector or a multivariate Gaussian if every linear combination of the xi's. So, a1, this is nothing but a1 x1 plus a2 x2 so on a n xn, if every linear combination of these x's is in fact Gaussian distributed. Okay. So, even if you find some vector a for which this is not Gaussian distributed, then x is not a multivariate Gaussian. So, maybe perhaps you can find, take it as an exercise in this case, try to find some a1 and a2 for which a1 x1 plus a2 x2 does not have a Gaussian distribution. It is fairly easy I think, because they have the same sign. So, you just have to figure out some a1 and a2 for which a1 x2 x1 plus a2 x2 is not Gaussian distributed. So, I mean in particular, okay, so you can take a equal to 0, right, and then you will get 0, right. So, you have to basically accept the 0 random variable as a very special case of a Gaussian with 0 mean and 0 variance. Okay. So, subject to that understanding, this definition is fine. Okay. Great. So, these three definitions are in fact equivalent. Okay. It can be proven. Actually, the proof is available in so MIT courseware, I think so lecture number 15 has as this material. Okay, lecture number 16 has a proof of the equivalence of all three definitions. Okay.
Vector x should be Gaussian for this to be multivariate Gaussian.
Correct.
With any other PDF we cannot make multivariate Gaussian, right?
No, see, so it is necessarily the case that, see, I can take a1 as something positive, or let us say a1 as 1 and all the other a's as zeros, in which case there has to be Gaussian. So, this definition clearly says that xi's are marginally Gaussian, but it says more than that, right. Any other questions? So, these three definitions are equivalent. So, another I mean just like in the 2-dimensional case, you can show that if the, so this covariance matrix V, as I said, contains all the entries as all the diagonal entries as variances and the covariances on the off diagonals. So, this is a positive definite matrix in general, and its eigenvectors which define a orthonormal basis for the space will again tell you the in which which directions the Gaussian will spread out more and which direction the Gaussian is not, is more compact, is more compressed, alright. So, this is in n dimensions, so we cannot draw it, but just the 2 dimensional analogy can be pushed forward. Okay. Also you can show that if the diagonal, if the matrix V has a diagonal structure, which means or the covariances are 0, then what you can show is that this will actually product out into, so V inverse will simply be, so it will be like the sigma 1 to the minus 2, sigma to the minus 2 and so on. So, if you expand this out, you will actually get a product of the marginal PDFs. So, which again means that if you have a diagonal matrix for your covariance matrix, that necessarily implies that the random variables are independent, right. So, generally uncorrelated entries, the entries in a Gaussian vector are uncorrelated, then they are all independent, which is generally not true, only for Gaussian vector is it true. So, even in this case, I mean there are some results about, see you can just like in the 2 dimensional case you can show that the conditional expectation is a linear function, okay. So, which means the MMSE estimate is a linear function of your observation. So, linear filtering is optimal is what these signal processing people like to say, right. So, linear filtering is optimal in the sense of MMSE for jointly Gaussian random variables. So, there is a couple of other cool facts maybe I should put down about these jointly Gaussians before I stop it. As you see, I am not spending too much detail on anything, I am just pointing out some interesting facts. So, if you have so, if we have x is equal to x1 dot 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 xn, let us say this is a multivariate, let us say this is a 0 mean multivariate Gaussian with covariance matrix V, okay. So, I am just throwing out the means because means are just a headache, right. You can, if they have non-negative non-zero means, just subtract it out, okay, subtract the mean vector out. So, in this case you can perform, so these guys are, so this x is, so the idea is to in some sense generate, so this x is given to you, alright, this is a multivariate Gaussian vector with some covariance matrix, okay. Now, we are going to generate uncorrelated or independent Gaussian random variables from here, okay. So, this, so the procedure is to do this, you take x1 w1 equal to x1, okay, then you take w2 equal to, so you take x2 and subtract out that, okay. So, you know that this error, so this is the estimation error in estimating x2 looking at x1, you know that this is orthogonal to that guy, right, but they are Gaussian, they are joint Gaussians, therefore, they are actually independent, not just uncorrelated, they are actually independent, right. And if you want to normalize it again, you can divide it by its variance, or you can make it unit variance if you like, but I can proceed like this, right. W3 I can write as x3 minus conditional expectation of x3 given x1 x2. So, so here again I am projecting, so I am estimating x3 based on observing x1 and x2, and again this error will be orthogonal to the subspace spanned by x1 and x2, correct, and so on, right. I can keep doing this. So, this is called, this is known variously as Gram-Schmidt procedure. In some people call this Gram-Schmidt procedure, signal processing people call it whitening. Okay. So, it is called, this is called whitening because so I mean I guess this is from the noise literature, right. So, you have this so you have this colored variable, so to speak, it has all these correlations, and then you have these W's are uncorrelated, and you can make it unit variance if you like. So, it is like in all these dimensions it has equal components. So, it is called whitening of this this excise, okay. This procedure is called whitening, and it is a causal procedure, right. So, I look at x1 and x2 and then decide my next W3 and so on, right. And since, see, one thing you should know is that if you look at this guy, this will be a linear function of x1 and x2 because conditional expectations are linear in whatever you observe, correct. So, this whole operation can be written as a vector W equal to L times x, okay, where L is a lower triangular matrix. Okay, so you see what I mean. So, this will only be a this will be a linear function of x1, this will be a linear function of x1 and x2 and so on. So, you have only a set of linear operations, and so W, so you can write this as a matrix form W equal to Lx, and because of this structure you get a lower triangular matrix, okay. This is called whitening matrix, okay. So, you can whiten these vectors, whiten this vector, and you can in fact show that covariance of the covariance matrix, right, covariance of x xx transpose or whatever. So, this was V, isn't it, can be written as L inverse whitening filter times B times L inverse transpose, which is the same as where B is a diagonal. This is a diagonal matrix. So, you can write this as L inverse B to the half, B to the half L inverse transpose. So, this will also be a lower triangular matrix, this will be an upper triangular matrix, okay. And so, this is like a triangular square root of your covariance matrix, okay. So, this is called Cholesky factorization, Cholesky decomposition. Anyway, so that is about whitening, which is again common in signal processing. Finally, the one another, so I will stop with one more little nugget about these multivariate Gaussians. So, you know that if you have just a let's say a single variate Gaussian, you know that the nth moment of the single variate Gaussian is only a function of mu and sigma, right, it is completely specified by mu and sigma squared. Similarly, if you have a Gaussian vector x1 through xn, all moments like expectation of x1 to the 4, x2 to the 13, whatever, any moment of any order can be figured out by just looking at the mean vector and covariance matrix, okay. So, the theorem that says this is called Wick's theorem, okay. So, let us say that, let us say x1 x2 dot 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 xn is a 0 mean, let us throw out the mean because it is just a headache, 0 mean multivariate Gaussian then expectation of, let us say I am going to write little y1 little, maybe I should write, maybe not, I should write maybe I should write expectation of y1 y2 yn equal to 0 for n odd, and expectation of y1 y2 dot 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 y2n. So, I am looking at an even product that is given by some pi expectation of yi yj. See these y, so the reason I switched from x's to y's, I did not do this as a mistake, each of these y's could be any of the x's. So, in y1 you can put x13, y2 can again be x13 if you like, okay, y3 can be x1, right, you can put it in any way you want. See these y's are some xi's, okay. So, if you have an odd product, because they are 0 mean, you will have 0, okay, and for the even case you will have all possible two-way products of these covariance terms, okay. So, this denotes all possible sums of these yi's taken 2 at a time. So, for example, if you want to compute, expectation of, let us say if you want to compute expectation of y1 y2 y3 y4, even with repetitions, y1 could be x1, y3 could also be x1, okay, even with repetition. So, this will simply be expectation of x1 sorry y1 y2 expectation of y3 y4 plus expectation of y1 y3 expectation of y2 y4 plus expectation of y1 y4 times expectation of y2 y3. Is that all? So, I have to take all possible, so I have 4 terms, I have to take all possible pairs, okay, and then add this all up, okay. And similarly, if I have, even for longer expressions you can do it, even if you have x1 to the x1 squared, x2 to the 4th, some x3 to the 6th, right, you will have to expand the whole thing out in terms of the covariance, these are all covariance matrix entries, right, and each of these y's are some xi's, okay. So, what this Wick's theorem says is, if you are given the covariance matrix, namely these entries, you can go ahead and compute any moment of these joint Gaussians, okay. So, this is called Wick's theorem, sometimes it is also called Feynman diagram formula, because Feynman used it in some calculation in his quantum field theory work, okay. He did not invent it, right, it was much older than him, but he used it, so it is called Feynman diagram formula. So, that is another nice nugget about this joint Gaussians. Yeah, so okay, that was my crash course on joint Gaussian random variables. Huh?
This n odd and n even.
Yes.
Can we interpret with geometry on why it is 0 and why this is some number?
So, no, it is very simple. So, you have y1 y2 blah blah blah, right. So, even if these are repeated, let us say I have y1 y2 y3. So, there is no way for me to take, so even so if I have y1 y2 y3, so y1 and y2 could be the same or different, but one of them will always have to be different. So, the expectation will be 0, but in the even case this may be like y1 squared y2 squared or x1 squared x2 squared, in which case I have to write all the x1 x1 x2 x2 x1 x2 x1 x2, right, all these possibilities I have to exhaust.